Oh, welcome to the stream. So today I'm going to continue working on the neural network I've been playing around with for a while. It's been 2 weeks since I last opened the project files, so this can be a bit confusing at first, but bear with me. Let's see, we're going to open up VSL Ubuntu here and look for the project files. I'm sure they're somewhere. CD coding. There I have some old folders. I think it's new NN. I hope. Let's see. This seems to be it. Let's see. Wait. What was I doing last time? Crap, I don't remember. Let's run everything. See what happens. Okay. Last thing I remember, it was working. Maybe not anymore. Let's see, what was I? Okay, so we can train the model one called fit. I'm gonna increase the size here for you. So we call the fit function to train it. We see the gradient suddenly becomes 0. Okay. We have the loss. Print out some bias, some neuron weights. Perform a prediction. Well, this is strange. What happened here? Maybe I've done some work on this somewhere else. I'm gonna see if I have a Git repository for this. Wait, maybe this isn't even a Git repository. No, it's not. Let's see. So I'm gonna do this off screen, look for the files. This seems to be it. Interesting. Interesting. So print out the gradients. Let's see where we do this. Okay, so in the backward propagation makes sense. How can the bias becoming the exact same? The bias should not become the same, and the weight should not become the same. So it's interesting. Maybe there's a pointer issue here. So during the back propagation, we adjust the weights and the bias of each neuron individually, and we do that, we say, concurrently, like at the same time. But it seems something is off there, because all here, for instance, the for the first hidden layer, the first neuron and the second neuron has the same bias. That's not right. That's not right at all. Task model for training. Evaluate it. Neurons, 0 weights. Okay. Let's clear up the debugging a bit. We can go to let's print out all the bias for the first layer, but the first hidden layer, the first dense layer here has 8 neurons. So let's instead go for this one. So I'm gonna take tail layer, previous layer, we're gonna print out the bias of the last hidden layer for debugging. It's to be compared after training. And when we do it here, it's to be compared with bias before training. I don't think we need to focus on the weights just yet. We can remove the prediction, those, the weights. That should be enough. Let's see here. Let's rerun this. Oh wait, something's wrong here. Oops. Typo. Then we have it down here as well. Oh. There we go. Okay, so we have the first 2 bias here. We are training the model, and he'll get gradient 0. Well, we know that gradient 0 it's not good. Well, it kind of is good, I guess, but it's not right. Wait, now I didn't adjust those bias. Interesting. So the bias in the last hidden layer remains the same. So something must happen for that. Let's analyze the first hidden layer. Like that, I guess. None. Oh, that's... What was the meaning of none? I forgot it. None, none. Ah, not a number. Wait, what? Why is it not a number? What happened? So the gradient somewhere became not a number. Okay. Maybe I should read through the comments, see if I left myself a clue or something before I went for vacation. Okay, so to do shuffle dataset, split up the dataset into training, validation, and testing. I think we're already doing that. Let's see, shuffle the dataset. We do that somewhere here. Dataset equals dataset.sample. Frac, what is that frac? I don't remember. Random state, is it random state? So that's about right. So we can remove that. This markdown is empty. Maybe it was this I was working on. That is my best guess. Scroll down. Welcome to the stream, by the way. I hope you're having a nice day. At least I am. Trying to remember what I did on this project before I went on vacation. Each day, net 1030, data flow, test data combined with int. But age should only be an integer. Let's see. No, it's a float, I guess. Sure. No, we're not going to convert to a numpary. We're gonna convert. Wait, should we just change the type of all of them to int64? Normalize. Wait, it's isn't that row? So normalize. What is it? Just future warning? Maybe it's fine. Not sure if it's worth fixing. is Mr. Okay. Can we just convert it? Oops. I was gonna suggest, yeah, just S-type in 64. But before I do that, I wanna explore that, see how it changes the data. Yeah, right. So it removes all the decimals, and that's not what we want, as I expected. Yeah, that's not right. So why is it complaining? Setting item of incompatible D-type is deprecated. Huh. Okay. But what? Where do we need to set it to int 64? If we run that block and this block. Wait. Oh, come on. Let's do it like that. Perfect. And type train x head. Can we do that? No, because it's not a pandas anymore. It's not pandas. Damn it. Let's type dataset head. Okay. There we should be able to do it. No? What? Why? Let's move this to a separate code block. Copy that. One more code block. Rerun all the previous blocks. Okay. Here we have normalized it. Complaints during the normalization. So it's just H. That's not. What are they? Other data types then? Let's see. Is it first all columns, then rows and columns? I think. How do we get the type? I don't think it's like that. Nope. Let's see what the Copilot has to say. Oh, just put inside type. Crap. Damn it. Dataset. What? Can we do it like that then? Nope. What the hell? I'm confused. Okay, so we first just print that. do that? It's invalid key. How is that an invalid key? Oh, because it's pandas. There we go. Course here, serious. Okay. Like so it's float 64. Like it probably said, turn the normalization, which I apparently removed. Now we're not getting the error. So the error is suddenly gone. What? Why? Okay, let's not dig into that. That's annoying. Okay. So I have some math here. With the ReLU, derivative of ReLU, MSE, derivative of MSE. We have neurons. And we have layers. We can remove this note, necessary. We have the model, we set cost function, we check the structure, we add layers, print layers, perform predictions, we have a test, backward propagation, with the fit function. We give it the training X, training Y. That's the attributes and the correct predictions, I guess. Validation X, validation Y. Let's see what to do with the validation. Nothing. We just used it to test. Seven, 9, 8. Seems like the bias here should just remain the same. What if I decrease the learning rate and rerun this? Okay. You see the gradient change here. I think I add like a limiter to the gradient, like upper and lower thresholds. Let's see. Okay, so backward propagation. We take the derivative there. We do the derivative of the activation function. Calculate the gradient and continue the backward propagation to the tail layer. We send the gradient and learning rates. Okay. let's scroll here. Yeah, this is dense layer. That's the first layer we'll reach. This output layer is the dense layer. So print out the gradient. We check if the previous layer is an input layer to select the correct result from it. So either X or A. This set to B is just equal to the gradient. That's how much effect the bias has on the gradient, on the result. We adjust each neuron here. Let's remember this place and scroll up to where we adjust the neuron, that function. Okay, so we have neuron should be before the layer. You have the adjust. We just subtract the learning rate times the weight gradient from the weights. Okay. We'll do the same thing with bias here. Straightforward. Let's clear some of the comments. Okay. Let's go back to this. We have I don't think see anything wrong in the neuron. So we go back to the backward propagation in the dense layer. This the A. The A to Z. Yeah, this math should be correct. We do some summations. This is strange. I have to check my Git because I'm pretty sure I did some more work than this. Up to 2 weeks. Wait, why is this not in a repository? Something is fishy. How do you check if we have current remote origin? We have the we are inside a Git repository. Okay, so let's reset everything. Git. How do you reset files? Git. It's like reset current head to specified state. Sure. Wait, no. Restore. Git restore. Now it's gonna. I must specify paths to restore. Sure, we can just restore NN. There we go. We restore the file. Now we're gonna pull the latest version. Okay. Let's see. Okay, so I have done more work. Like I say, it's. I knew there was something. There was something to it. Because the first started, I solved the disappearing gradient. Okay, so. Okay, I'm pretty sure I left this somewhere like in a working state. So check the backward propagation here for the dense layers. We see, oh right, there was some different math here. We had to adjust the math, now remember. And then we did some clipping to the gradient to prevent it from becoming too large or too small. We also had to, here we still grab the output from the previous layer, but then we do the dot product here between the gradients and the inputs that we transpose, divide by the amount of entries, since we're using mean square error, which builds on like the mean value of the errors. So if I run this now, I think it will work. As you can see here, this was the output last time. So we start off with this loss and end up with this loss. We do have an improvement. Maybe it's not great. Let's clean up some of the some of the outputs here. Set the cost function. Check the weight. We don't want to check the weights. We just find model. Perfect. Do we need to clean up something else? We can. Right, I basically refactored most of the code for went on vacation when I was sitting at the library, because I felt like I had kind of mixed up the columns and rows for the two-dimensional arrays. So I fixed that, and also I fixed like smaller errors in the math. Well, major errors, I guess. Because if I hadn't fixed those, then we would still have the disappearing gradient problem. And disappearing gradient problem, let me bring that up for you. So here we have it like the phenomenon where gradient diminishes as they are propagated backwards through layers. So it makes it difficult for models to learn up the weights, especially in deep networks, which is what we have here. Since we have hidden layers, we like have so many layers, we can't really just understand what's going on without really analyzing it thoroughly. Let's see, maybe this describes it. I'm not sure what they mean here, but I think, yeah, like here's a pretty good explanation. So this one we want to see the gradient the whole way, but what we have done now is like what the problem we had was that the gradient was disappearing step by step as we did the backward propagation, and by the like after a few runs or just a few layers, it was suddenly zero. which means if we head to 0, we can't adjust anything due to the math behind it all. So if you look at we go to the neuron, and here we see this is where we use the gradients. We have the weight gradient, the bias gradients. But if these are 0, then we will just subtract, well, 0 from weights and bias. So we'll stop adjusting the network. Okay, so let's rerun everything. We'll run from top down here. So we have this network, and we define the cost function, mean square error. We perform a test, and this test is done on the validation data, same as this. So basically this is the loss. So we can actually do it like this. Print formatted loss before training. Let's call the test function instead with the whole validation set. There we go. And now we're gonna fit it 4 times. Basically, we're gonna train 4 times. I do this way. You can probably do better, but it's just so I have something to test with. Okay. And what just happened? What the hell? Interesting. What? Did I break something? Did I do anything at all? What? So I think I know what is going on here. I might know. Shit. I think it's because we might be storing the outputs of so when we do a prediction, I also store the output of each layer, which I use for the back propagation. So if we predict something, which we do during the test, let's see, we have it right here. We do predictions. That might be used during the training. That's why if this one is turned on, it might have some problems. Sometimes, not always. Okay, so if we count this out, it works. Now it works all the time. No, not all the time. Okay. Crap. But still, let's take a look at that. So we do the fitting. We first grab the data. X. True. It's called X set, so it's not yellow. I don't like the formatting. And we then do the prediction. So let's follow the prediction. Why was that one yellow though? Parameter X NA. Wait, can it be NA variable constant? It's because It's capital. Oh. Okay, and here it's parameter since it's defined as parameter. So let's follow the naming convention instead. So never just a single capital letter, or basically no just capital letter unless it's a constant. There we go. Convert to a numpy array. Check the length. We check the input shape, make sure that's correct. Then we perform the prediction of all of them at the same time. Okay. And so we go to the head layer and perform forward. The head layer is input layer. That's the head layer. Okay. I just noticed that you guys might have heard the music through my headphones as well. Like, I'm playing the music for you, but also that you might have heard the music picked up by the microphone from my headphones. I'm sorry about that. So let's get back to it. Okay, so then for propagation, we store the x here. So overwrite old value. That's good. We initialize it as none. That's fine. We go to dense layer, and during the for propagation, we store the values. So we overwrite the old values. That is fine. You do see neural network stuff. You do. You are not mistaken. So I've been on vacation like 2 weeks and just forgot about where I was in this project. So I'm still a bit confused about what is going on. I can understand all the steps, but I don't really remember why I had some issues with it. Yeah, maybe the hype has died down a bit, but it's still fun to play around with. Like 1 year, I'll probably start a master in machine learning. So I thought maybe it's a good idea to start diving deeper into it right away to get a good head start. Oh, in 3 years. Why haven't you? Like, haven't you been required to do it in your work, or have you used something else? Maybe just large language models or something? Like, I feel like most people just smack a large language model onto every problem. Like, oh, it's a math problem, large language model. Or it's you need to extract some data, large language model. Just, oh, you don't need it. Yeah, I guess it makes sense. Yeah, I mean, don't people usually use cloud computing for large language models anyway? Like, I think, well, you know, Microsoft Azure and Amazon and Google all have some services that provide the computational power and storage. Like the new model that Meta just released, you know, the new Llama model. I think the parameters for that one, the weights and biases, takes like 200 gigabytes. Oh, you rent Google supercomputer for it, yeah. Well, how is that via? It's called Firebase. Google Firebase. Yeah, is it via Firebase to do that? Oh, it's via Google Cloud probably. Huh. Cloud, let's see. Google Cloud is getting more expensive though. Aren't all of them? I heard that the whole like remote hosting and serverless solutions are kind of getting out of hand, that they're not really worth it anymore. I might be wrong. Oh, or also maybe the price is increasing because more people use it. You know, they have like just letting the customers who can pay the most. Store the outputs of each prediction. And after each prediction. Wait, what? Just start to build your own supercomputer. Hold up. I need to know more. Tell me about this. This sounds awesome. Just start to build my own supercomputer. How do you build your own supercomputer? Like, are you rich as fuck, or are you building like a GPU farm? Or maybe you're doing it in Minecraft, like everyone else. Yeah, I can imagine building a quantum computer being quite hard. I actually saw an article on how to write a neural network for quantum computers the other day. I haven't read the article yet, but it would be super fun to do it and like read the article and see if it's something I can do. I also heard that some companies give you access to their quantum computers to play around with a bit, just to explore the subject more, like for the overall understanding. I realized. Oh, nice. Well, do you work in IT? I assume you do. May I ask what you do, by the way? Like, more specifically? You don't actually. But what do you do then? Like, if you're, you seem to be quite into the whole AI field, and you make good money. So, like, what do you do? Oh, VTuber agency. Okay. Huh. Must be fun, I guess. Maybe. Is it? It's fun as hell. Nice. I'm glad you enjoy your work. It brightens my day. It's so sad when people hate their work but just stay there and continue doing it. Like most of their lives, it's horrible to see. Like, I have family members who have done that, like been in the same company for like 40-50 years. Wait, not 40-50. 40 years actually. Who's suffering there. Oh no. Wait, click save. Click save on what? Oh. I get it. Huh. Well, some people are just a bit too stressed out at work. They don't even know how. Wait. Are you talking about your colleagues who doesn't even know how? Because if that's the case, then I feel sorry for you. It must be frustrating to have such colleagues. Oh, the VTubers. They gotta learn. They must learn. They can't always rely on you. Maybe they can, I don't know. Maybe they pay for that support. Because if they do, then I can imagine you making good money. I think someone else joined us in the chat, by the way. Welcome. Let's see. Where was I? I was doing the back propagation, the fitting for each of those, do prediction, the back propagation. This is fine. Let's see. Every VTuber it is. I don't know. Maybe they are. I can't really tell because I haven't probably analyzed them and I've worked with them either. So, but I have actually been working with YouTubers back in the days when I worked at a video production company, and we edited videos for like a wide range of YouTubers. Some of them were very special to work with, not very pleasant, to be honest. They were like, as you described them, kind of stupid, really. Oh, dot rom just lurking while seeing. Yeah, I'm still playing around with neural networks, .romb. I've been away for 2 weeks, so I haven't really had the time to continue what I was doing. Oh, this neural network isn't really meant for anything specific. It's right now I'm using a data set on concrete compressive strength. It's just a data set that was given for an assignment for an AI course. It's extremely small data set, just 1030 entries. But the goal with this, what I'm doing right now, is to get a deeper understanding for how to build neural networks from the ground up. And I was actually thinking about changing this data set to something bigger. Because 1030 entries, that's not even close to enough. Yeah, wait. Shouldn't I be using this type of file anymore? The Jupyter notebooks. Wait. Oh, you never understood it. Well, it's super convenient for when you are learning things and just playing around. But for production, not so much. I think though there's a way to use it in production. I think you can like convert it into just simple Python files. I might be wrong, but I think you can. .romb, no, I'm not making a regression model to predict the next stock crash. I'm sorry. I will let you know when I do that. I don't think I will ever do it though. Maybe it would be fun to try it, just as an experiment. But you know, I don't have the type of data, and it's basically impossible. Well, it's impossible until OpenAI does it. Wait, what? Why did you let an AI control your PC for a month? What did it do? Did you like set it up to do your work for you? Or was it an experiment? You have some interesting stuff to say. So it's just like clicking around. I hope this was on a virtual machine. Wait, what? Oh crap, what, they had access to your Twitter? Damn. Huh. Like, if you have any quotes that it tweeted, it would be fun to read. Just maybe post one here in the chat. I want to see it. Oh, it's .romb. You don't like notebooks? Oh yeah, I understand what you mean, .romb. I agree with you. It's not super convenient when you have too much code, unless I would say unless everything is connected and you have to execute all the cells of code, which I'm doing here. But if I were to expand this project, then I would probably have to separate the code into unique files, you know, separate the concern. But then I would probably do most of the development from a notebook, so I could see the output, but I would still have just normal Python files at the side. You tried giving the AI emotions. Huh. So, was the AI happy? Like, what did it feel when it was posting on your Twitter? Pipeplot. Wait, is it Pipeplot? Oh, well, dark humor is good humor. It's the purest of all humor. Matplotlib. I always forget how to use the Matplotlib. I don't know why. It just never sticks in my head. It is Pipeplot. Why is it? Cannot be resolved. Let's be lazy. Okay, so I was thinking about plotting the loss here. I have to I need to save the loss though. Right, if any of you haven't subscribed yet, make sure to do that, because I assume you enjoy watching me struggle with this. And I would still love to see one of the quotes from the AI, like what he posted on your Twitter. Let's see. Oh, thank you so much. It is fun because you know exactly how they feel. So we do a test here. That's the loss. Okay, so let's call this loss history. And set the loss history, append, do the validation, loss history. Can we like select the last element like that? Let's see. Your Twitter account is banned. Oh no. Sorry to hear that. Well, you can create a new account now on X, as they call it. Still not a big fan of that name. But Dotrom, I have played around with RNNs, just not in this way. I have used the TensorFlow for that, if I am correct. Yeah, I have. I did that during a course when we were supposed to predict weather, you know, classic example. It would though be fun to do it again with bigger data set. Oh right, you're asking that because of the stock market thing. Yeah. I see that there's data sets on it's called Kaggle of specific stocks, I think. Let's see. Is it Kaggle? Yeah, let's search for Nvidia. Nope. Stock market data set. Is it Nasdaq? Yeah, it is. Oh, this would be fun to play around with. Awesome. How much does it cover? Dates, open, high, low, close. It's per day. Daily prices. Okay, so it's not like you can't really use this for day trading predictions then. Okay, 8,049 entries. Wait, that's it? No, that can't be right. This is considered blah blah. List available Nasdaq. Huh. Roses, red, violets, blue. I hate you. I'll throw a brick on you. Oh my god, that's beautiful. That's a beautiful quote by the AI. So wise. I really like looking into Rose Deep Filter Net. Wait, what? What is that? Deep Filter Net. No complex speech. Oh. Defiltering. Huh. That's cool. There's paper on it. Wait, so does it uses deep learning for speech enhancement? Yeah, that makes sense. And noise suppression. Isn't this like CPU heavy? Because I can imagine it's quite a lot of calculation that has to be done in the background, and maybe the audio might get out of sync. What? Noise suppression somehow mutes me instead. Oh, whoa, use RNNs for that. That's awesome. Just, I should explore this sometime then, because sounds cool. Licenses. Let's see. There's a paper. Ah, of course it's Arxiv. It's always here. They have all the papers. Wait. The paper on this is just 2 pages long. This is the shortest paper I have ever seen. Maybe it is enough though. Like abstract introduction, deep filters. Wow. My settings are obviously not that extreme, but huh. Wow. Can run my 8121U CPU. I don't remember what generation that is. Wait, it's an i3? I mean, running this on an i3 might be a stretch. Yeah, I doubt it will work great for you. Like this combined with Chrome, and your computer would maybe crash. I don't know. Give it a try and let me know if it works. You would fry that little ship. It would die in a week. But maximum temperature 105 makes sense. But it's still DDR4. DualShock 2018. Maybe. I don't know, it's risky to try. You don't have integrated graphics. Wait, you're running that CPU with a GPU? Isn't the U series also for laptops? Yeah, it's soldered on. Wait, so you have a... So you're running a like laptop or something like this? Yes. Yes and yes. Okay, so something like this, I guess. I'm not sure what the answer to. Maybe I should get back to the coding. I don't know. It's so fun to talk to you guys. X-label epochs, that makes sense. And Y label is lost, yes. Sure, we can have title. Do we have to call the show function? Spin all open figures. No, we do not need to call show. This is an interesting curve. We have all kind of. I got it from a laptop motherboard and modified it to desktop motherboard. Oh, cool. GPU I need to use. Huh. So I guess you connected the GPU via the small PCI Express connector on the laptop motherboard. Because that's the only way I know how to do it. If that even works, I don't know. So, wait, you plot the... you usually plot two things, I think. It's the... hold on. You also... like when you look for underfitting and overfitting, is it training and the test? I think So you like plot the loss of the training and test against each other. I want to throw on it. You had to add the connector. Damn, that's hardcore. I want to throw NVIDIA GTX 408. That's old. That is very old. Wait, so RAE. I'm using a mean squared error for this. If that's what you were asking. Damn, all these ads. So I have validation loss and train loss. So you have to store both of them and compare, I guess. Let's go to the model and add a self dot. Let's call this train loss. Loss history. That. Down to the fitting. And I was gonna store the train loss. Are we gonna now when we're gonna pass the training data into the loss function, should it just be the set we just trained on or all of it? Oh, yeah, I'm sorry about the confusion there. So right now I'm just gonna print out the loss of the validation set against the training set, just for fun, you know, look for overfitting and underfitting. But I'm thinking like for the loss of the training set, should it be calculated with all the training data after each epoch, or just the training data used for that epoch? No, it should be useful, right? Okay, I'm gonna use all the training data for each like history entry. So we're gonna type self dot train loss history append. We're gonna test train X, train Y. We're gonna type train self dot train loss. We're gonna take the last entry, val loss. Okay. Now when we run this, we'll have way more output, sorry. Yeah. That looks good. And Here we're gonna have to plot these two now against each other. How do you do that? How do you do that? I am horrible at the matplotlib. Wait. Oh, maybe you are a neural network. Maybe you are GPT-4o? Is it called 4o? I'm not sure about the model numbers anymore. They are hecka confusing. Like, they release a new GPT every week now. Okay, maybe not, but you know. If you keep track of the AI news, you see like a new model at least once a week. The last one launched was the new Llama by Meta. I'm gonna do a quick Google here just to see how to use the matplotlib. Let's go with your schools. I like this website. It's super simple, as you all know. Oh, we can just wait. We have the X and Y. Yeah. What if we want to plot two lines on the same? Markers. No, we don't want to add markers. We want multiple lines. No. Oh, here we go. Oh, you just plot both of them. What? Sure. We have balance 1, 2, 3. 1, 2, 3, 4 values. I guess so. So veloc, PLT, plot, train loss. How do you add labels to them? Labels. Okay. Wait. GPT-4o is trash. It's trash? Is GPT-4o really that bad? Is that the lightweight version? No, it's Google keeps translating everything for me. Do not translate, please. Yeah, it's the mini version. Oh, but I mean, it makes sense that it's not as good because it is smaller. I'm pretty sure it has some use cases too. But seriously. Okay, I have no idea what I'm doing. Yeah, I barely have an idea either. Add axis labels, or are you talking about? I'm talking about the curve labels. I want to add the curve labels. And where do I do that? Do you know what is it, like? What is it called? OT. Oh, okay. Thank you so much. Wow! Perfect. You're my savior. Okay, let's see. So, wait. I don't see the names of them. Do I have to call PLT show anyway? Oh. Oh. Okay, so I added the label here, like you said, but it doesn't print here. Why not? You need a legend. Oh wait, that is the little box, right? With all the names. Oh yeah, okay, now I remember. Yeah. Thank you. Maybe I should take like a online course on Matplotlib. I feel like I need that. So the validation, it prefers better on the validation than the loss, but still seem to have a problem here with the gradient. Okay, so here we jump around a bit. And then better. Suddenly barely moves. I mean, it does move, but barely. So maybe this one's redundant. It's a bit too much training. Huh. Okay. Yeah, I will wait for you. In Cineroar HP Frunner. That's quite the username. By the way, .rom, if you feel like the music is too loud, please let me know. Let's see, what should we do to improve this? I'm taking some inspiration from a YouTube playlist right now. A guy who built a neural network, also from scratch, like the same thing, ish. To see what additional functions he implemented. I'm thinking about adding dropout for better generalization. I think that's how you say it. See the whole playlist by this guy. Let's see what we have. Layer dot products, batches layer objects, layer softmax activation, calculate loss. Oh no, apparently the the playlist I was looking at by a YouTuber was not really what I thought. Like, his additional videos was just him going a bit deeper on each of the basic subjects. You could also try a simpler autoencoder on MNIST or STD. That should be simple enough. Try simple autoencoder. Oh, SH something. Thank you. Yeah, but I think I'm gonna wait with the CNN's MNIST and try to improve this a bit. I think I want to add dropout Don't you use Dropout for regression problems too? And maybe also add normalization. Wait, what was it called? TensorFlow. It's called L2 or something. Regularization. Okay, I'm gonna have to take a quick break, like 3 minutes. So please wait for me, and I will be right back. I am back. An autoencoder can also just use a simple dense layer, especially. Yeah, that's true. That's very true. I could do that layer, but then also have to add the what do you call it? Cross entropy loss. Is that what you call it? Adding softmax shouldn't be a problem though. Yeah, cross entropy loss ish. What? It should be fine. Well, you're talking about not tackling it as a simpler regression, no, as a classification problem, more like a regression problem. So you want it to be like the output to be just the number of it, or because cross entropy loss just measure the difference between the output. Just measure the difference. Wait, I'm not sure I follow. You just measured the difference. What? Encode decoder part. Difference between output and inputs. The autoencoder is supposed to construct it. I have to Google this. I don't think I've done this before. Huh. Image. Okay. First picture is basically what I imagined an autocomplete. This one? Yeah, it makes sense. It would be fun to do this. Like, what is the real use case of it? I guess for this type of classification. What's it called? I remember what it's called. Let's see, and use cases. Oh, maybe this is a good article. Workflow to dirt, it's management. Here we go. Dimensionality reduction, image denoising, generating image times. Wow, this is cool. The idea is that you compress the input using dimensions. Then we have encode decode and extensively. Wow. What? I'm definitely gonna write this down because I want to explore this later. So first, I want to be able to classify MNIST and then encoder and decoder. Or do that. Oh, that's some cool ideas. Thank you so much for telling me about this. I think I read about it in a book a while back. Autoencoder. Oh, that's true. Ah, that's awesome. Wait, so yeah, that is what they use for the like I said, the that's what they use for denoising and stuff. That's awesome. But if I'm gonna do that, Do you think a CPU is enough for it? I have a pretty old CPU, I'm afraid it might be a bit heavy for it. Maybe I need to make use of CUDA cores. It should be enough. Oh shit. Oh, have you done it? Oh yeah, for Emnis should be enough. Yeah, that's true. That's true. I was thinking about the example image I saw where they used the Mona Lisa, and that's probably a bit much. What is it like? You have 4 dimensions per pixel. No, not 4 dimensions, but 4 values per pixel. Maybe that's a bit much. Was one of the first things? Oh, one of the first things to learn. Cool. Was it on your own or was it for a course? On your own, that's cool. That's impressive. I assume you used something like TensorFlow or PyTorch for that, or did you also do it from the ground up, like I'm doing? I use PyTorch. I've never used PyTorch myself. I use TensorFlow, but what is your experience with PyTorch? Like, is it intuitive? Is it like well thought through? Should I explore it sometime, or should I just stick with TensorFlow? Oh. Yeah, I see that here. They say it's a bit better for that type of work. So maybe I should explore it. Huh. But even definitely had to build whole pipeline first. That is true. Like when you start the training, it's kind of doing its own thing. And for the pipeline as well. I remember when I was using it, I had to. I was working a lot with the data. What do you call it? Data generation, like where it converted and generated augmented data. And there I had to add a bunch of printing to keep track of what was happening, but that's still not really the same thing. So PyTorch might be worth exploring sometime. And way easier. I mean, Keras and TensorFlow aren't really complicated, but PyTorch, if that's even simpler, that's awesome. I wonder, does it have support for CUDA? Probably does, yeah it does. Okay, maybe I should get back to this. You're too interesting to talk to. I'm like, oh, it's hard to keep focus. So I was thinking about, as I mentioned earlier, I want to improve this before I move away from it. And oh my god, Kappa. Who is that guy even? I don't know who all these characters are that you guys send pictures of. I'm not up to date with the latest emojis. Ex-Twitter employee. Okay. Like, what's the meme about it? Behind it? It's one of the OG emojis. Wow, I'm not sure about that. Maybe. I feel like I'm a bit behind on the whole internet culture now. I'm not up to speed anymore. Too old. I was just wondering about the math behind the dropouts. Introduction, blah blah blah. What is dropout? The term dropout refers to dropping out of nodes, implementing layers in a neural network, as in Figure 1. Yes. All the forward and backward connections with the dropped node are temporarily removed. Thus creating network architecture out of the parent network. The nodes are dropped by dropout probability of P. Input from a dropout layer with probability P. During the forward propagation, during training, from the input X, I just want to drop that come. Okay. Okay, so in the drop layer will basically just set some of the outputs to 0. So when you drop a neuron, I guess it's just the same thing as setting the value to 0, the output is 0. Let's see, sorry, I gotta see what you wrote. This one with the OG emojis, yeah, I'm talking about Twitch. Oh, Twitch emojis, okay, got it. Like, can I send any cool emojis? Oh yeah, the dancing dino. This is my favorite right now. It's beautiful. It's art. Right, so we solved the overfitting with the dropout layer. What do we do in overfitting? Overfitting would be if the training performs way better than the validation. So we don't really have an overfitting problem here. So maybe adding dropout is not what we should be doing. Maybe we should add early stopping. Let's see. Also, I think there's some form of early stopping in each during each epoch. Also, like if it has, if it's on the first epoch starts to get worse results, that it stops them. Alright, here we have the early stopping. Yeah. Simple, effective, use approach for training, stopping. Yeah. That's what I understood about it. So I guess I will wait with that, since I'm not really suffering from a overfitting problem. It's more like a just performance problem. I think, but wait, does dropout increase the performance? Maybe it does. Okay, here the first mention, regularization, dropout regularization, early stopping. Okay, so what if I try to add these? L1/L2 station. After that, add dropout. Oh. And we're not going to do data augmentation. We're not going to be adding noise, early stopping. There we go. And early stopping. So let's say we run during the 10th epoch. The results start becoming worse. Should we then stop? I don't think we should do that. We should stop the rotation starts to increase, model loss starts to increase. Should we stop the training? Stop training model. Okay, so we stop training model. That's like the early stopping, isn't it? Yeah, early stopping. Okay, so we want. Oh, yeah. Okay. Then I guess regularization. That's on the schedule. That's what I'm gonna do. And what is the difference between L1 and L2? Let's see. No. Universal problem with machine learning has been making an algorithm performs equal well on trained data and any new samples or test dataset. Techniques used in machine learning that has specifically been designed to cater to reduce test error, mostly at the expense of increasing training error, are globally known as regularization. Train set, line regression, without regularization, with. Okay. That's interesting graphs. math behind it. Here we might have something. L1, and we have L2. More specific gradient descent. Okay. Spares. Wait. Glias. Huh. Okay, okay. Huh. So I'm not gonna do the dropouts. Wait, I'm lost. Ah. Wait, so we changed the we changed the mean square error, the loss function. Oh. The original model they used. Realization. Okay. Bridge regression as squared magnitude. Class function. Here the box part. Alter. Wow, that's simple. Different usage importance, blah blah blah. Oh, summary. Sum of absolute values of weights, sum of square weights. Yeah. Okay, so square all the weights and sum them together. Okay. Sparse output, non-sparse, more segmented out solution. Multiple solutions are possible. Only one solution. Built-in features like feature. Yeah, we're gonna go with L2 regularization. Let's verify that here. And we're gonna add. Oh, welcome back. I'm exploring how I should add L2 regularization. I hope you had a nice break. I'm not sure what you were doing, but I'm happy you're back. So here we have the error function and we add that. So do we need the regularization? Is it also added during the backpropagation? Given AI emotions again. Oh my god, poor AI. How did it feel? Was it depressed? Huh. Add to layer. Let's go to layer. It's only the dense layers that will have the regularization functions. And I'm gonna create a function here, set it should be private. Yes. L1, L2. So we're not gonna add L1 anyways. We can remove that. Convert to lowercase. That is correct. And then set regularization function, we call self set regularization function, we pass it the regularization function. Oh, let's see what you wrote, sorry. And welcome back to the stream, whoever just joined. Oh, just welcome to the stream, sorry. He doesn't even know it's an AI. I'm just recreating the human. It sounds complicated. What tools do you use for that? For trying to simulate the human brain. L2. Let's stay there. Scroll up here. Find the math. Add L2 regularization. Math behind that was not too complicated. It's just this. So we take lambda, we square, wait, and that's number of neurons to sum them up. Okay. Define L2, we will have weights lambda. Wait, you can't call lambda. Right, because it's for lambda functions. Let's call it lam. and just gonna return lum some, we square them. This is correct. So here we square each weight, this part. We sum it, the summation sign, we multiply it by lambda here. Perfect. Wait, I'm just recreating the human brain, my own brain. Wait, what? I'm just recreating the human brain, my own brain laws. What? What? No, I mean like you are. You're confusing me right now. Are you or are you not writing code? Maybe you're just doing something weird on paper. Retrace point to small. Okay. The cost function. Wait, what? The regression model that uses autoregress is called regression. I thought they added L2 regularization just to layer, but you do. So is that for each layer? So for each N should be for each neuron. Okay, I gotta read through this. As penalty to the loss function. But if lambda is very large, they will add too much weight. It will lead to underfitting. Okay. Okay. So, in short, I'm just copying my brain by reading off my neurons. Oh, I think I understand what you're doing then, yeah. Sounds awesome. So you have one of those things you put on your head that like reads the brain activity. We are gonna okay, here we have the math. This is the good stuff. Yeah, sure. I'll wait for you. Autoregularization, one of the most popular techniques in machine learning, is a method to reduce the variance of the model and increase bias to make it more generalizable. Okay, L2 regularization is a map estimation with Gaussian prior probabilities due to the imposed prior. The model can generalize data well by scaling the weights as per their significance. Okay. The L2 regularizer objective functions and its gradient is given by okay. From Taylor series expansion, we'll make a quadratic approximation, blah, I can't read, of the unregularized objective function. V is the minimizer of the unregularized objective function. So I guess use an alpha. Okay, so square it. Multiply by lambda with the cost function. Why do you divide by 2? Okay. V star is the minimizer of the unregularized objective function. I'm kind of lost here. We have L2. Like, are we supposed to? I need a better understanding of it. Where is it implemented exactly? Maybe I wish I had my old book that covered this. Sure. Accept all the cookies. We do love the cookies. Okay. This might be of interest. I'm gonna pause the music, play this video.
L2 norm to the loss function. It regularizes the sum of squares of the weights. So if we add L2 norms to a linear regression model, it becomes the so-called ridge regression. And here's, okay, let's move forward to L2 regularization. L2 regularization as L2 norm to the loss function. It regularizes the sum of squares of the weights. So if we add L2 norms to a linear regression model, it becomes the so-called ridge regression. And here's its objective function. The first term, again, is the mean square error of a linear regression model. And the second term is the L2 norm. Alpha here again is a hyperparameter we need to tune, and it controls the amount of shrinkage. The larger the value of alpha, the greater the amount of the shrinkage of the weights. Here's a diagram showing ridge coefficients as a function of alpha. On the x-axis, we have alpha decrease from 10 to the negative power of 3 to 10 to the negative power of 9. And on the y-axis, we have the weights. So here you can see when alpha decreases, the weights increases from 0 to over 200 or decrease from 0 to negative 100. It means that if we increase alpha, we look at the x-axis from the right to left, then the weights will approach 0. That's how alpha controls the strength of the regularization. Now let's also look at the geometric interpretation of L2. For L2 norm, the isosurface looks like a circle or a disk, which indicates the quadratic regularization term. The combination of W1 and W2 cannot fall outside the disk. If we only focus on minimizing the penalty term, then the optimal...
Okay, so let's see where I use the loss function. That's mean squared error. So that is only during the loss. I'm sorry about all the noise from my phone. There we go. Okay, so sounds like you need. Yeah, you could hear the phone vibration. Okay, I'm gonna resume the music, I think. So, we add this to the mean squared error. So during, wait, do you use it for prediction? No. During fitting, activation function. MSE. You think it's too loud? The keyboard noise? Right, the cost function. There's a cost function. Test. And the also need to use for the backward version. Oh, yeah. If you don't mind, maybe other people also don't mind. I personally find it kind of soothing to hear keyboards. Like it's kind of cozy to hear the switches. Unless the person is writing too fast. So we have the cost function, propagation. Squares of the weights. Rhythmus keyboard. I like more subtle, deeper thumping. Maybe. I don't know. I'm not 100% satisfied with the sound of this keyboard. It would be nice with something smoother, like something that's a bit more soothing, in the fashion that it's like the sound shouldn't be so sudden. Maybe a bit quieter too, I guess. One day I might get a new keyboard. I don't know. Just for streaming. So this is confusing as hell. So we add the L2 penalty to the loss function. But then function there. What do you call the cost function? Let's go to the beginning. We set the cost function. Use for the test, which is compare the values. And just I personally find it very hard to find a new keyboard that I enjoy, that feels with switches that feels right for me. So this keyboard took me almost a year to find, and the keyboard I had before that I used for maybe 4 years. But that one was kind of trash, to be honest. This one was actually recommended to me by a keyboard enthusiast in the store, and he was like, oh crap. It was like, you should try this one out. I personally love it. So I was like, sure. I wasn't convinced at first because it was kind of expensive, but then after a while it kind of grew on me. But now, 1.5 years later, wait, 1.5 years, I think it's even older than that. Anyway, a while later, I didn't feel as comfortable with it as I had in the beginning. It's I don't know, maybe I should stick with it just a while. But anyway, I'm afraid I gotta go now, but I'll make sure to do more research on the L2 regularization before next stream, because I feel kind of stuck again. So stuck that it's probably not so fun to watch me struggle. But I thank so much for watching this stream, and I hope you have a great day. I'll see you around.